We have been talking about how to calculate the work done on very simple kinds of objects, works by individual forces and net force, the net work done on an object, as it moves. We're going to want to consider, as the chapter goes on, more complicated kinds of objects, things that aren't so rigid. So here I'm imagining a system consisting of several objects connected by forces. I'm imagining four different masses. Some of them are connected by springs, and the springs are visual representations of forces. We're going to imagine that whole mess in some initial configuration and then later on in some final configuration. That's complicated, and so we're going to wait to treat that case. We will get to it later on in the chapter, but we're going to try to start simple. So let's go a little bit simpler. Here is a system that consists of a single rigid object which can translate and or rotate between the initial and the final configuration. That's still not the simplest because of the rotation, so we're going to even back up a little bit more and imagine a system consisting of a single rigid object which can only translate. In other words, it doesn't rotate at all, it only moves without rotating. That's what translation means. Physicists sometimes call that kind of motion the motion of a particle. I know in everyday language people tend to use the word particle to represent something that has sort of a negligible size, something that's really small, but something like a book can behave like a particle in the sense that if it only translates, particles have no sense of rotating because they're so small there's nothing to rotate. So something that doesn't rotate and behaves rigidly, we sometimes call it in physics a particle. So this is a particle, and we're going to analyze the motion of a particle and relate the net work done on it to something else that's interesting. Okay, so we'll start here with this case. Later on in the chapter, we'll get to this most complicated case. Okay, now in the motion from the initial to final state, there's always, so I'm imagining here's the displacement of maybe the middle of the object up there, there's the displacement vector. There's always lots of forces that act on it, and I'm just going to denote those forces just qualitatively by red force vectors here. So those are supposed to be the forces, and we're going to assume for now that those forces are constant all the way through the motion. So the forces that are acting are constant, unlike that discussion we had a little bit ago with the area under the curve. We're back to constant forces. If all the forces are constant, that means there's a resultant net force which is constant during the motion. So there's a constant net force being applied to it. Now if there's a constant net force, there's a constant acceleration. If there's a constant acceleration, that means the velocity of this thing is changing. If the velocity is changing, that means the initial velocity is probably different than the final velocity. So I've denoted those initial and final velocities by somewhat randomly oriented green vectors here. The initial velocity changes as it goes to the final state because there's a constant acceleration happening if the net force is non-zero. Now, we're going to want to apply what we know about constant acceleration kinematics, our kinematics equations, because we're treating a case of constant acceleration here if the net force is constant. To use those kinematics equations, we got to break up into x and y components. So let's choose x, y axes. I chose horizontal and vertical. And then once we've got those axes, we can visualize what the components are of the force vector. Here's the x component and the y component, the displacement x and y components, and the final velocity x and y component, and the initial velocity x and y components. We can break all those things into x and y components, and we're going to apply constant acceleration kinematics. Net force is constant all the way through this motion, and therefore the acceleration is constant. So we can use our third kinematics equation, the one with the v squareds in it, for both the x components and the y components there. First thing we're going to do is relate that acceleration to the net force by using F net x equals max and F net y equals may to express ax and ay in terms of F net x and F net y, like that. Then we're going to add these two equations together. And when we do that, so we're going to add the left-hand side, and that will be equal to the sum of the right-hand sides. And when we add the left-hand sides, we're going to get Vx final squared plus Vy final squared. That's the sum of the squares of the two of the x and y components of a vector. When we add the sum of the squares of the x and y components of a velocity vector, we just get the speed of that vector squared. So the sum of this side is just the square of the speed, the final speed of the object. The sum of these two things squared is equal to the initial speed of the object. And the sum of these two things is kind of a mess, so we're going to leave that for a second. Okay, final speed squared, initial speed squared when I sum those two, and then here we've got a common factor of 2, so I factored it out in front of some parentheses. Now the thing in parentheses is almost equal to the net work done on the object. The net work done on the object during this motion, as we've seen before, is the net force x component times delta x plus the net force y component times delta y. This is equal to that in the parentheses there. It said we've just got a 1 over m, a common factor of 1 over m. So I can write this as the net work done on the object during the motion divided by m, and let me make that replacement up here to simplify this equation. And now let's just simply solve for the net work. The first thing I'm going to do is divide everything by 2 and multiply by m. When I do that, I get this. The v squareds get an m in front of it and a 1/2 in front of them. And then solve for w net. We find that the net work is equal to 1/2 mv final squared minus 1/2 mv initial squared. And we're going to make a definition now to just write that in a slightly different notation, and that is, as you saw in the reading, we define the kinetic energy of an object of mass m moving with speed v to be 1/2 mv squared. And so this is the object's final kinetic energy, and this is the object's initial kinetic energy. And so we have this relationship, which is so important I put a box around it and it gets its own name. We'll call it the work kinetic energy theorem. Some other people sometimes call it the work energy theorem, but we're going to have different kinds of work energy theorems in our class. So let's be clear about this one. This one only relates the net work to the kinetic energy change of the object. So net work done on an object is equal to the final kinetic energy minus the initial kinetic energy. Not completely obvious to begin with, but that's why it's called a theorem. And we are going to apply this in certain cases shortly. So just to summarize, we're assuming the system moves as a particle. This wouldn't be true if it didn't move as a particle. In other words, if it weren't rigidly moving without rotating at all. And in that case, the net work is equal to the change in the kinetic energy. And in fact, even though we assumed the forces were constant, this relationship is true even if the forces are not constant. Here's a little argument for that. Let's imagine again that we apply it just during a tiny little displacement. In that case, the net work, since the force is approximately constant here, in other words, the red curve doesn't change in height too much in this little period here, so we can approximate it by the flat curve there. That would be a constant net force, and calculate the net work using that. And so that net work would be equal to the change in kinetic energy in this little region, and also in this little region and this little region. The net work is equal to the change in kinetic energy for all these regions, and if we add all those up, what we get is the net work done by all the forces on it is equal to the area under the fx versus x curve, we already talked about that, is equal to the change in the kinetic energy. So this W net equals the change in the kinetic energy is true even for non-constant forces. All right, keep that in mind. We won't do those cases too often, but occasionally it might come up, and you certainly read about that too. All right, so let's keep in mind we're going to take a break and then do some voting questions and then some problem solving. But the one thing that's extremely important is that this result only applies to motion of a particle or particle-like motion where something doesn't rotate and moves rigidly.